wonder about the possibility of life on other planets. Well, we're taking a deep dive into a discovery that could completely change how we think about that.
Intriguing.
It's called dark oxygen, and it's pretty mind-blowing.
Dark oxygen. Okay, I'm all ears.
So for the longest time, we thought photosynthesis was the only way oxygen was made, right? Plants using sunlight and all that.
Right, the classic equation.
Mhm.
Sunlight, water, carbon dioxide, and voila, oxygen.
But this new research is suggesting that might not be the whole story.
Really? Now that's fascinating. Tell me more.
It all started with Professor Andrew Sweetman and his team from the Scottish Association for Marine Science. They were out exploring a part of the Pacific Ocean known as the Clarion-Clipperton Zone.
Ah, the Clarion-Clipperton Zone. Isn't that the area that's attracting a lot of attention from deep-sea mining companies?
Exactly. It's known for these metal-rich nodules on the seafloor.
Right, the nodules. Lots of valuable metals there, the kind that are used in electric car batteries and all sorts of tech.
So, picture this. Sweetman and his team are sending down sensors to measure oxygen levels, expecting the usual readings. You know, the kind you'd find in a typical deep-sea environment.
Makes sense. Go on.
But then, things take a turn. They start picking up these unexpected increases in oxygen where there really shouldn't be any.
Wait, hold on. Increases in oxygen in the deep ocean where there's no sunlight? How is that even possible?
That's what they thought too. Initially, Sweetman even thought his instruments were malfunctioning. He couldn't believe what he was seeing.
Wow, that's wild. It really shows you how deeply ingrained our assumptions about oxygen production are.
It does. But he double-checked everything, and the readings were real. They had to find an explanation.
So how did they rule out other possibilities like, trapped air bubbles or leaks in the equipment?
They went through all of that. They were meticulous. They ruled out every other possible explanation they could think of.
What were they left with?
Well, eventually, they started to suspect that the nodules themselves were producing oxygen. They even took it back to the lab to test their theory.
Hold on, the nodules. Those metallic lumps on the seafloor. How could they possibly be making oxygen?
Think of them like natural batteries. They create a small electrical charge. And they believe this charge can split water molecules, like breaking them apart.
Ah, electrolysis. We did that in high school chemistry class. But I never imagined something like that happening naturally on the ocean floor.
That's pretty incredible, right? And when you split water, what do you get?
Hydrogen and oxygen. Okay, that's starting to make sense now. But I bet not everyone is convinced by this explanation.
You're right, not everyone is buying it, especially some of the groups involved in deep-sea mining.
I can see why they might be skeptical. If these nodules are producing oxygen, it could throw a wrench in their plans, right?
Yeah, exactly. One group in particular, the Metals Company, has been pretty vocal. They're suggesting those oxygen readings could be from things like, again, trapped air bubbles, leaks in the equipment, the usual suspects.
So they're not ruling out the possibility of errors in the measurements?
Not at all. They even pointed to one of Sweetman's control experiments. He had a chamber with just seawater in it, and the oxygen levels rose there too.
Oh, that seems like it would contradict the idea that the nodules are the source of the oxygen.
Right. But Sweetman has a response to that. He says the way they filled those chambers might have actually introduced the extra oxygen.
Introduced it. How so?
Well, they injected cold surface water into some of them, and that cold water could have carried in oxygen accidentally.
Ah, so it might have been a contamination issue.
Exactly. The key is, in the chamber that didn't get the injection, the oxygen levels remain stable.
Okay, so that weakens the Metals Company's argument a bit.
It does. But they also had another critique. They pointed to a figure in Sweetman's research paper that showed apparent oxygen production in a chamber that didn't have any nodules present.
That sounds like a pretty significant oversight.
It was an error, and Sweetman acknowledged it. But he pointed to the presence of manganese granules in the sediment of that chamber.
Manganese granules. What do those have to do with anything?
Well, those manganese granules are also found in the nodules themselves, and Sweetman thinks they might be acting similarly to the nodules, producing that extra oxygen.
So even without the nodules, there might be other things in the sediment contributing to the oxygen production.
Interesting. Right, so we've got this potential new source of oxygen in the deep ocean, and there's a lot of debate swirling around it. The question is, where do we go from here?
Well, to get to the bottom of this, Sweetman and his team have secured a 3-year research project funded by the Nippon Foundation.
Wow, so they're really going to dig deeper into this, literally.
They are. And they're even building special deep-sea landers that can reach depths of 11,000 meters.
11,000 meters. That's incredible. They're really pulling out all the stops for this.
They are. They want to try and replicate their findings in other areas of the Clarion-Clipperton Zone, and they want to nail down the exact mechanism behind this dark oxygen production.
So more data, more analysis, more experiments. Sounds like they're on the right track.
They are. And they're also looking into whether hydrogen is being released during this process, which would further support the water splitting theory.
And that could have implications for the microbial life down there, right? If there's hydrogen available, could microbes be using it as an energy source?
Exactly. They're planning to study those microbial communities as well to see what role they might be playing in all of this.
This is getting more and more complex. But it's also super exciting. This dark oxygen discovery could change how we think about life on Earth and maybe even beyond.
You're absolutely right. The implications are huge. If dark oxygen can exist here on Earth, it opens up all sorts of possibilities for where else it might be happening.
Like on those icy moons, Europa and Enceladus, we talked about those earlier. Places with water, but no sunlight.
Precisely. Scientists, especially at NASA, are starting to consider that very possibility.
Okay, so we've got this incredible discovery with huge implications, but we can't ignore the other elephant in the room. The whole debate about deep sea mining happening in the same area.
Yeah, that's a critical piece of the puzzle. Those metal-rich nodules that are potentially producing dark oxygen are also what those mining companies want to get their hands on.
It's like we're at this crossroads. On one hand, we have this potential new source of energy, a possible key to understanding life beyond Earth. And on the other hand, we have this push to exploit these deep-sea resources before we fully understand them.
You've hit the nail on the head. It's a tough situation. It's going to be fascinating to see how this all plays out. What stands out to you the most so far? What really grabbed your attention?
For me, it's the sheer audacity of this discovery. For centuries, we thought we had oxygen figured out, and now we're realizing there's this whole other process going on right under our noses.
I completely agree. And that's what makes this deep dive so captivating. It's a reminder that there's still so much we don't know about our own planet, let alone the universe. We've got a lot more to unpack here, so in the next part we'll delve into the critiques of Sweetman's research and explore those alternative theories about where this dark oxygen might be coming from.
Welcome back. I'm still trying to wrap my head around everything we talked about in that first part. Dark oxygen, nodules acting like batteries. It's a lot to take in. But one thing that struck me is that not everyone's on board with that whole electrolysis explanation, right?
Yeah, and that's a good thing. Science thrives on skepticism and rigorous testing, so it's not surprising that there are alternative theories out there about where this dark oxygen might be coming from.
Okay, I'm really curious about these other explanations. What are some of the ideas researchers are exploring?
Well, one of the more intriguing ones involves radioactivity.
Hold on, radioactivity. Down in the deep ocean, how does that tie into oxygen production?
It all goes back to the Clarion-Clipperton Zone itself. Remember, it's not just those metal-rich nodules down there. The area also contains small amounts of radioactive elements, like uranium.
Right, right. I vaguely remember something about radioactive decay from my science classes, but it's been a while.
Well, the basic idea is that when those radioactive elements decay, they release energy. And that energy can actually split water molecules, releasing oxygen as a byproduct. It's a process called radiolysis.
So instead of the electricity from the nodules, it's the energy from radioactive decay that's splitting the water.
Exactly. It's definitely a possibility worth considering, and it's something scientists are actively investigating.
Okay, so we've got electrolysis and radiolysis on the table now. Are there any other contenders in this dark oxygen mystery?
There's one more we should talk about, and it involves our old friends, the microbes. We touched on how they might be involved in facilitating the electrolysis process, but some scientists believe they could be directly involved in producing oxygen through a completely different mechanism.
Okay, remind me again, how are the microbes thought to be helping with the electrolysis?
The initial idea was that they might be somehow interacting with the nodules, maybe helping to create that electrical charge, or perhaps using the hydrogen released during the splitting process as an energy source.
Right, right. But you're saying there's a different way they could be involved.
Exactly. There's this process called dismutation. It's a bit complex, but basically it's a chemical reaction where a single compound gets transformed into two different compounds.
Okay, bear with me. I'm trying to follow. How does this dismutation thing relate to microbes and oxygen?
Well, some scientists believe that certain types of bacteria could be taking nitrogen compounds found in those deep-sea sediments and, through this dismutation process, converting them into oxygen.
Wait, so they're not splitting water, they're actually creating oxygen from other elements.
Precisely. It might sound crazy, but there's actually evidence to support this theory. Scientists have found similar bacteria producing oxygen in other extreme environments, like deep underground aquifers.
Wow, so we've got electrolysis, radiolysis, and now dismutation, all as potential explanations for dark oxygen. It's like a scientific whodunit. How do researchers even begin to figure out which one, or maybe which combination, is actually happening?
Well, that's where Sweetman's new research project comes in. Remember those high-tech deep-sea landers they're building?
Oh yeah, the ones that can go down to those incredible depths.
Exactly. Those landers are going to be loaded with all sorts of sophisticated sensors, allowing them to not only measure oxygen levels, but also hydrogen levels, search for those radioactive elements, and analyze the types of microbial communities present. It's about gathering as much data as possible to try and crack this case.
So it's like a deep sea detective story, and they're using these landers to collect all the clues.
That's a great way to put it. Each piece of data they gather helps paint a clearer picture of what's going on down there and brings us closer to understanding the true source of dark oxygen.
This is fascinating stuff. But it makes you think about the bigger picture. If dark oxygen can exist in these harsh, sunless depths of our oceans, could similar processes be taking place on other planets or moons?
Now you're thinking like an astrobiologist.
Yeah.
And you're absolutely right. That's one of the most exciting implications of this whole discovery.
I mean, I've always been intrigued by those icy moons out there, like Europa and Enceladus. We know there's water beneath their frozen surfaces, but without sunlight, we always assumed life would be impossible.
That's precisely why the dark oxygen discovery has scientists at NASA and elsewhere so excited. It's like a whole new window of possibility is opened. What if these moons, or other celestial bodies for that matter, have similar processes happening?
Life fueled by chemical energy alone, not needing sunlight at all. That just blows my mind.
It's a total game changer. And it highlights just how much we still don't know about the universe and the incredible diversity of life that might be out there.
Okay, so much to think about there, but let's bring it back down to Earth for a minute. We're talking about the Clarion-Clipperton Zone, which also happens to be the place those deep-sea mining companies are interested in, right?
Right. The very nodules that might be producing this dark oxygen are also the targets for those mining operations. And that creates a pretty big dilemma.
Exactly. So on one hand, we have this potential new source of energy and maybe even a key to understanding life beyond Earth. And on the other hand, we have this drive to extract those valuable resources before we even fully understand what we're dealing with.
It's a classic clash between scientific curiosity and economic interests. A tough situation with no easy answers.
I mean, do we prioritize getting those metals, even if it means disrupting these ecosystems that might be playing a crucial role in supporting life in a way we don't fully understand yet? Or do we hold back and potentially miss out on those resources?
It's a delicate balance. There's no simple right or wrong answer here. But I think it underscores the importance of approaching the deep sea, and really any natural resource, with a sense of respect and responsibility. We need to think about the long-term consequences of our actions.
That's a really important point. It's not just about what we can get, but also about what we might lose in the process. And it makes me wonder, even if Sweetman and his team ultimately prove that dark oxygen is real and figure out exactly how it works, does that automatically give us a free pass to start mining in those areas?
I don't think so. Even with a complete scientific understanding, there are still major ethical considerations to grapple with. We're talking about potentially disrupting these unique ecosystems that might be playing a vital role in supporting life in ways we're just beginning to understand.
Wow, this conversation has really got me thinking. So much to ponder. Out of all the things we've discussed so far, what's really stuck with you? What has stood out the most?
For me, it's that sense of wonder that this whole discovery evokes. The fact that we can still make such groundbreaking discoveries, things that completely overturn our understanding of the world, even in places like our oceans. It's just amazing.
I completely agree. It's a good reminder that there are still so many mysteries out there, hidden in the depths of our planet and beyond. Who knows what other incredible secrets are just waiting to be uncovered?
Exactly. And that brings us to the last part of our deep dive, where we'll explore the future of this research and consider what the ultimate implications of dark oxygen might be.
Okay, so we're back for the final part of our deep dive into this incredible world of dark oxygen. We've talked about the science, the controversies, the ethical questions it raises, and even the potential for life on other worlds. It's a lot to process. But I'm really curious, where does this all go from here? What's next for dark oxygen research?
Well, as we've been saying throughout this deep dive, we're really just at the very beginning of understanding this phenomenon. There's so much more we need to uncover.
Right. So what are the big questions that scientists are focusing on right now? Where do they go from here?
One of the most pressing questions is determining the exact mechanism or mechanisms behind dark oxygen production. Like we discussed, there are several possibilities: electrolysis, radiolysis, dismutation. It might even be a combination of factors at play.
So how do they tease apart those different processes?
That's where things get really exciting.
Yeah.
Researchers are developing even more advanced sensors and analytical techniques to really get down to the nitty-gritty of what's happening at a chemical level.
And I imagine those deep-sea landers we keep talking about will be crucial to all of this.
Absolutely. Those landers are going to be our eyes and ears down in the Clarion-Clipperton zone, allowing us to continuously monitor oxygen levels, hydrogen levels, map out the presence of those radioactive elements, and collect all sorts of samples.
It's like having a permanent research lab right on the seafloor.
Exactly. And with all that data, we can start building more accurate models of how dark oxygen is produced, how it interacts with the surrounding environment, and how it might be contributing to those deep-sea ecosystems.
And then those models could even be applied to other environments, right? Like those icy moons we've been talking about, Europa and Enceladus. It's amazing to think that what we learn in the depths of our own ocean could help us understand those distant worlds.
It really is. By understanding the processes at work here on Earth, we can start to make predictions about whether similar things might be happening elsewhere in the universe.
It's like a whole new way of looking for life beyond Earth. Instead of just focusing on planets in the so-called habitable zone, we might start looking for places with the right chemical ingredients for dark oxygen production.
Exactly. It expands our search in ways we never imagined before.
This is all so mind-blowing. We started with this seemingly simple idea of oxygen being produced in the dark, and it's led us to these incredible possibilities. It feels like we're witnessing a whole new chapter in the story of life being written.
It truly is remarkable, and it reminds us just how much we still have to learn about our own planet.
Well said. So, as we wrap up this deep dive into the fascinating world of dark oxygen, what's the key takeaway you want our listeners to remember?
For me, it's the fact that our understanding of life is constantly evolving. What we once thought was impossible oxygen production without sunlight is now a reality. And this discovery has opened our eyes to a whole new realm of possibilities for where and how life might exist.
Absolutely. It's a reminder to stay curious, keep exploring, and to never stop questioning what we think we know. So to everyone listening out there, if dark oxygen can exist here on Earth, defying our expectations of where oxygen can be found, well, what other seemingly impossible processes might be shaping our planet and the universe beyond, the most incredible discoveries might be just around the corner waiting for us to uncover them.